Far from the warm light of ordinary stars, there are objects whose entire existence depends on a balance that cannot be seen. A neutron star may hold more mass than the Sun within a sphere only a few dozen kilometers wide. Its gravity has already done nearly everything gravity can do to matter without sealing it behind an event horizon. Atoms cannot remain intact there. Electrons and nuclei no longer keep their familiar distance. The interior has been pressed into forms that have no lasting counterpart on Earth, and yet the collapse has stopped. That pause is the beginning of our story. It is not a comfortable pause, and it is not an empty one. Every layer remains under compression. Every particle contributes to a strata that must answer gravity continuously, not once, but through every second of the star's long existence. A neutron star is not suspended by heat in the way a living star is supported by energy flowing from nuclear fusion. It has no steady furnace, replacing fuel in its center. It can cool for millions of years and remain a neutron star. Whatever holds it together must continue working even as its surface fades and the remnant becomes harder to detect. The answer is not one force acting alone. It is a layered agreement between quantum mechanics, nuclear physics, and gravity described by general relativity. Each part of that agreement matters. Remove one, and the object we call a neutron star may no longer be possible. Gravity presses inward through every layer. The particles inside respond through rules that do not come from temperature or ordinary rigidity. Neutrons cannot all settle into identical quantum states. Nuclear interactions change as particles are forced closer together. Pressure rises with density, but in Einstein's theory, pressure also adds to the gravitational field it is trying to resist. The star survives inside that complication. Seen from a distance, it may announce itself as a pulsar, sending regular beams across space as it rotates. Some spin slowly. Others turn hundreds of times each second. Their signals can be measured with remarkable precision, but the object producing them is hidden beneath kilometers of material no telescope can look through. The surface gives us only the outermost clue. Beneath it lies a crust of compressed nuclei and electrons. Deeper down, neutrons begin to move outside nuclei. Farther inward, familiar nuclear structures may dissolve into dense quantum fluids. At the center, the true composition is still uncertain. The matter may remain mostly nucleonic, or it may contain particles and phases that cannot survive under ordinary conditions. This uncertainty does not mean that nothing is known. It means the neutron star has become a laboratory provided by nature, one that operates at pressures no terrestrial machine can maintain. By measuring mass, radius, rotation, cooling, and the gravitational waves released. When neutron stars merge, physicists are learning how strongly dense matter pushes back. Those measurements are slowly narrowing the range of possible interiors, but the central question remains simple enough to carry through the entire journey. How can matter resist gravity after gravity has already crushed it beyond atoms? To answer it, we will move inward rather than forward. We will pass through the crust, into the quantum fluids below, and toward the unresolved physics of the core. We will follow the forms of pressure that do not depend on heat, the nuclear interactions that stiffen matter, and the relativistic gravity that makes every layer harder to support. Somewhere within that structure lies a limit. Below it, matter can still hold a shape. Above it, the shape is lost, and a black hole begins. A neutron star begins long before the collapse, while its parent star is still shining. For most of its life, a massive star survives through a balance that is easier to recognize than the one inside the remnant. Gravity pulls inward. Energy released by fusion creates pressure that pushes outward. As long as those two effects remain matched, the star keeps its broad shape, even while its interior changes from one fuel to another. Hydrogen burns first, then helium. In the most massive stars, later stages can fuse carbon, neon, oxygen, and silicon. Each stage is shorter than the one before it. The star is not simply using up a single reservoir. It is rebuilding its center again and again, raising the temperature, opening a new chain of reactions, and delaying collapse for a little longer. Near the end, the interior becomes layered. Different shells burn different fuels at the same time, with the heaviest products collecting toward the center. The deepest region becomes rich in iron group nuclei. That is where the sequence changes. Fusion has supported the star because lighter nuclei can combine and release energy. Iron sits near the peak of nuclear binding energy. Combining iron into heavier nuclei does not provide the same outward energy source. Once a sufficiently massive iron core has formed, the center can no longer replace the pressure it is losing. The core is already dense enough for electrons to play a major role in supporting it. Those electrons are packed into a quantum state similar, in principle, to the one that supports a white dwarf. But as the core grows, the electrons are driven to higher energies, and the margin of support becomes smaller. Then, the conditions begin to undermine the support from within. Energetic photons break some iron nuclei apart. This process absorbs energy rather than releasing it. At the same time, electrons are forced into protons inside nuclei, producing neutrons and neutrinos. Electron capture reduces the number of free electrons available to provide degeneracy pressure. The core does not merely run out of fuel. It loses the structure that had been holding it up. Collapse begins. The inward motion is so rapid that the outer parts of the star cannot adjust in an ordinary way. The central core falls inward through thousands of kilometers, becoming smaller and denser in a fraction of a second. Matter accelerates to a significant fraction of the speed of light. Nuclei are squeezed together. More electrons combine with protons. Neutrinos pour from the changing matter, though at first many of them become trapped by the immense density. As the center approaches the density of atomic nuclei, the behavior of the material changes again. Nuclear interactions become strongly resistant to further compression. The innermost core stiffens, and the collapse there slows abruptly. Material still falling from above strikes this newly resistant inner region. A shock wave forms and begins moving outward. This is often described as a bounce, but the word can make the event sound simpler than it is. The shock immediately spends energy breaking apart the heavy nuclei it encounters. It also loses energy through neutrino emission. Left on its own, it can stall before it escapes the star. The final explosion depends on a more difficult exchange of energy. Neutrinos emerging from the newly formed compact core pass through the region behind the Stulge. A small portion of their energy may be absorbed by the surrounding matter. Convection, turbulence, rotation, magnetic fields, and the structure of the original star can all influence whether the shock is revived. The broad picture is well established, but the detailed path from collapse to explosion remains one of the most demanding problems in stellar physics. The event unfolds through matter that is too dense, too hot, and too dynamic to reproduce as a complete system on Earth. When the shock succeeds, the outer star is driven into space as a core collapse supernova. Elements formed before the collapse are carried outward. New nuclei can also be created in the expanding debris and in the extreme environment surrounding the remnant. The compact core remains behind. At first, it is called a proto-neutron star. It is hotter and larger than the older neutron star it may become. Neutrinos are still trapped within much of it, and they carry away an enormous amount of energy over the first seconds. As the remnant loses that energy, it contracts. This cooling is not like a warm object resting in a room. Most of the energy leaves as neutrinos, particles that interact so weakly that they can pass through matter that would stop light completely. In those first moments, The neutrino emission carries away much of the gravitational binding energy released by the collapse. The remnant also inherits rotation. A stellar core may have turned only slowly before the collapse, but when its radius shrinks by orders of magnitude, conservation of angular momentum can make it spin far faster. The same principle appears when a skater draws in her arms, though the scale here is much greater. A newborn neutron star can rotate many times each second. Its magnetic field is compressed as well. Magnetic flux that once passed through a stellar core thousands of kilometers wide is gathered into a much smaller area. Rotation, fluid motion, and dynamo processes during collapse may strengthen the field further. The result can be a pulsar, or in some cases, a magnetar with an even more intense field. None of this guarantees that the object will remain a neutron star. The outcome depends partly on how much mass is left in the compact core. If the remnant is too heavy, it may collapse into a black hole almost at once. In other cases, the explosion may begin successfully, but material that was initially pushed outward can later fall back. That returning matter adds mass to the remnant and may force a delayed collapse, so the birth of a neutron star is not a single instant with a simple boundary before and after. It is a sequence of transitions. A supported iron core loses its pressure, a collapsing center reaches nuclear density, a shock forms, stalls, and may be revived. A hot proto-neutron star sheds energy through neutrinos. The remaining object contracts toward a colder, more stable configuration. By the time the remnant settles, the familiar architecture of atoms has largely disappeared from its interior. The star that once survived through heat and fusion is gone. What remains must be supported by a different kind of physics. The next layer of the story begins at the surface of that remnant, where matter is already compressed beyond anything found naturally on Earth, and where every step downward changes what matter is allowed to become. The surface of a neutron star is not where the strangeness begins. It is only where the strangeness becomes visible. From far away, the star may look like a point of X-ray light. Up close, there would be no familiar landscape, no soil, no ocean, no atmosphere in the ordinary sense. Gravity presses everything downward so strongly that any loose material settles almost immediately into an extremely thin layer. The outermost surface may be made from hydrogen or helium, if the star has gathered material from a companion. In other cases, heavier elements may dominate. Beneath that skin, however, the pressure rises so quickly that matter is forced into a sequence of changes. The first major region is the outer crust. Here, atomic nuclei still exist. They are arranged in a rigid lattice surrounded by electrons that move through the structure. The arrangement is sometimes compared with a metal, but the comparison reaches its limit almost at once. The density is far higher. The electrons are strongly degenerate, and the nuclei are pushed into forms that ordinary matter cannot sustain. Near the surface, iron group nuclei may be present. Deeper down, the growing pressure changes which nuclei are most stable. Electrons are squeezed into smaller volumes and forced into states of increasing momentum. Their energy rises even if the star is no longer very hot. Under these conditions, some electrons combine with protons inside nuclei, producing neutrons and neutrinos. The nuclei become increasingly rich in neutrons. This is not a random process. At each depth, the matter tends toward the arrangement that minimizes its total energy under the local pressure. One kind of nucleus gives way to another. Proton numbers decrease, neutron numbers rise. The material moves farther from the combination found in stable place on Earth. For a while, the nuclei can still contain the added neutrons. Then they cannot. At a density of roughly 400 billion grams per cubic centimeter, the outer crust reaches a boundary known as neutron drip. The name describes what happens with unusual clarity. The nuclei become so neutron-rich that some neutrons are no longer bound inside them. They begin to leak out into the spaces between nuclei. The star has entered the inner crust. The matter here is a mixture. Neutron-rich nuclei remain in a lattice, but they are surrounded by free neutrons and degenerate electrons. The free neutrons are expected to form a superfluid. A superfluid is not simply a very smooth liquid. It is a quantum state in which large numbers of particles behave in a coordinated way. The fluid can move with almost no internal friction, and its rotation is organized into thin quantized vortices rather than the broad swirling patterns of an ordinary fluid. This hidden superfluid may help explain some of the most revealing behaviors seen in pulsars. A pulsar can rotate with remarkable regularity for years. Then, without warning, its rotation rate may increase slightly. Astronomers call this event a glitch. The change is small, but the timing can be measured with great precision. One leading explanation involves the superfluid inside the crust. As the solid crust gradually slows through electromagnetic radiation, some of the superfluid may retain a slightly faster rotation. Its vortices can become pinned to structures in the crust. Stress builds between the two components. When many vortices shift or unpin, angular momentum can be transferred to the crust. The surface rotation speeds up, and a distant radio telescope records the event as a sudden change in pulse timing. The glitch is not a direct image of the interior. It is an inference built from timing behavior, models of superfluidity, and the known physics of rotating quantum matter, but it offers one of the rare ways to study motion beneath the surface. Deeper within the inner crust, the nuclei are pressed closer together. Their shapes may begin to change. At lower densities, nuclei tend to be nearly spherical, because that form balances competing nuclear and electrical effects. As the spacing between them narrows, the balance shifts. The attraction between nucleons and the electrical repulsion between protons begin to favor more complex structures. Spheres may stretch into long rods. Rods may join into broad sheets. At still greater densities, the arrangement may invert, producing tubes or bubbles within a more continuous background of nuclear matter. Physicists refer to these possible structures as nuclear pasta. The informal names include spaghetti, lasagna, and other shapes suggested by the geometry. The names sound light, but the material they describe may be among the strongest known forms of matter. Chemical bonds do not hold these structures together. Chemical bonds belong to the scale of electrons moving between atoms. Here, atoms have already lost their ordinary identity. The structures arise from nuclear interactions acting across material, packed close to nuclear density. Computer simulations suggest that nuclear pasta could be highly resistant to deformation. It may influence how the crust cracks, how magnetic fields evolve, how heat moves through the star, and how oscillations pass from one layer to another. Its exact form remains uncertain. The calculations are difficult because the system contains enormous numbers of interacting particles. Different models do not always predict the same shapes or the same thickness for the pasta region. Some suggest that it occupies a meaningful fraction of the inner crust. Others allow a narrower transition. What matters is the broader physical movement. The deeper the descent, the less useful the idea of separate nuclei becomes. The lattice begins as a collection of identifiable nuclear objects. At greater pressure, those objects distort, merge, and lose their boundaries. By the base of the crust, matter is approaching a transition into a more uniform fluid. The entire crust may be only about a kilometer thick, perhaps somewhat more or less depending on the star's mass and equation of state. Compared with a radius near 12 kilometers, it is a thin shell, yet it supports mountains, stores elastic strain, guides magnetic fields, and interacts with the superfluid beneath and within it. A mountain on a neutron star would not resemble a mountain on Earth. Because the surface gravity is so strong, Even the highest stable irregularities may rise only a small distance above the surrounding crust. But a tiny asymmetry can matter when the star rotates hundreds of times each second. If the mass distribution is not perfectly balanced, the rotating star may emit continuous gravitational waves. Detectors have searched for these signals from known pulsars. A confirmed detection would reveal how much the crust can deform and how evenly matter is distributed inside the star. The crawl still break in a highly magnetized neutron star, especially a magnetar. The magnetic field can place stress on the solid outer layers. A sudden rearrangement may fracture or shift the crust and release energy through bursts of X-rays or gamma rays. The word fracture can suggest two pieces separating cleanly. Under neutron star gravity, the reality is likely more complex. The crust may shear, crack, and rapidly settle into a new configuration, while the magnetic field and internal fluids respond. Even here, in the region that most resembles a solid, the star behaves as a connected system. Rotation couples the crust to the superfluid. Magnetic fields thread through charged particles. Heat moves outward from deeper layers. Stress accumulates and is released. Every observable change at the surface carries information from material hidden below. At the bottom of the crust, the last recognizable nuclear structures fade. The lattice disappears. The remaining nuclei merge into the surrounding matter, and the star enters its outer core. There most of the mass resides. The material is no longer a solid framework with neutrons moving through it. It becomes a dense quantum fluid dominated by neutrons, with smaller populations of protons, electrons, and perhaps other particles. The crust shows how pressure dismantles atomic structure one stage at a time. The core reveals what resists after that dismantling is complete. Below the crust, the neutron star becomes fluid. There is no sharp visual boundary that a traveler could recognize. The change is written into density, pressure, and the kinds of quantum states available to the particles. The last distorted nuclei dissolve into matter that is more continuous, and the outer core begins. Most of this region is made of neutrons. Protons and electrons are present in smaller numbers, with their proportions set by reactions that move the matter toward beta equilibrium. If too many neutrons occupy one condition, some can transform through the weak interaction. If too many protons and electrons occupy another, the reverse process can occur. The composition settles into a balance that depends on density. The neutrons do not behave like tiny solid spheres stacked beneath the crust. They form a degenerate quantum fluid. The word degenerate has a special meaning here. It does not describe decay or disorder. It describes a collection of particles whose lowest available quantum states have been filled. Once those states are occupied, additional particles must enter states with greater momentum. This comes from the Pauli exclusion principle. Neutrons belong to a family of particles called fermions. Electrons and protons belong to the same family. Identical fermions cannot occupy the same complete quantum state at the same time. The rule is not a physical barrier positioned between particles. There is no hidden shell surrounding each neutron. It's a part of the mathematical structure of quantum mechanics, and it shapes the behavior of matter from ordinary atoms to collapsed stars. In an atom, the exclusion principle prevents all the electrons from gathering into the lowest energy level. Instead, they fill orbitals in an ordered sequence. That arrangement gives atoms their layered electron structures and makes chemistry possible. Inside a neutron star, the same principle operates under far greater compression. Gravity tries to place an immense number of neutrons within a smaller volume. The states with low momentum fill first. Once they are occupied, the remaining neutrons must enter higher momentum states. As the matter is compressed further, the range of occupied momenta extends upward. The particles carry motion even when the material is cooled as far as quantum mechanics permits. That distinction matters. In an ordinary gas, pressure depends strongly on temperature. Heat the gas and its particles move faster. Cool it and they slow down. A neutron star may begin its life at an immense temperature, but the pressure that supports it does not vanish as it cools. Degeneracy pressure comes from crowding in quantum state space, not from thermal agitation. One way to picture this is to imagine a long building in which every room can hold only one person of a particular kind. The rooms nearest the entrance are occupied first. As more people arrive, they must climb higher, entering rooms that require more effort to reach. Making the building smaller does not allow two people to share the same room. It forces the occupants into a wider range of higher levels. The analogy is limited because quantum states are not physical rooms, but it captures the important point. Compression cannot place every neutron into the same low-energy condition. The exclusion principle requires the collection to retain a spread of momenta, and that spread produces pressure. This pressure resists gravity throughout the outer core. It is sometimes presented as the single answer to what holds up a neutron star. That answer is incomplete. If the neutrons were treated as a non-interacting quantum gas, degeneracy pressure would still appear, but a model built only from that effect would not reproduce the heaviest neutron stars that astronomers have measured. The particles interact at the distances found inside the core. Nuclear forces contribute greatly to the pressure. Their behavior is more complicated than a simple attraction or repulsion, and their contribution changes with density. At moderate separations, the interaction between nucleons helps bind atomic nuclei. At shorter separations, the effective interaction becomes strongly resistant to further compression. This repulsive behavior adds stiffness to dense matter. The exclusion principle and nuclear interactions cannot be cleanly separated inside a real neutron star. The available quantum states influence how particles move. Their interactions change the energy of those states. The composition adjusts. The total pressure emerges from the full many-body system. There is no single row of neutrons carrying the weight of the layers above. Pressure acts locally. At every depth, the material responds to the conditions around it. Deeper regions support the pressure of everything farther out, but each part of the star must also remain in equilibrium with the gravitational field at its own position. The center experiences the greatest pressure. Gravity there does not pull in one preferred direction because matter surrounds the center on every side. Even so, the weight of the entire overlying star creates the highest compression in that region. Density rises inward, and the equation describing pressure must rise with it quickly enough to prevent collapse. In a less compact star, Newton's description of gravity can provide a useful approximation. In a neutron star, it is not enough. General relativity changes the balance. Mass and energy curve space-time. Pressure also contributes to that curvature, the same pressure helping the star resist. Compression adds to the gravitational field that makes resistance necessary. The result is not a simple contest in which pressure grows until it matches gravity. A rise in pressure provides additional support, but it also strengthens the source of gravity. Near the maximum possible neutron star mass, this feedback becomes crucial. More compression demands more pressure adds more gravitational influence. The star approaches a point where no stable arrangement can be found. Far below that limit, the balance can endure for a very long time. A neutron star does not need to spend fuel to maintain degeneracy pressure. It can radiate away its remaining heat, slow its rotation, and fade from view while its quantum support persists. Its particles do not become inactive. Neutrons near the top of the occupied state distribution still carry tremendous momentum. Protons and electrons occupy their own degenerate systems. interactions continue throughout the fluid, the temperature can remain high by human standards and still be low compared with the characteristic quantum energies of the core. Under those conditions, neutrons are expected to pair. Although an individual neutron is a fermion, two neutrons can form a correlated pair whose combined behavior resembles that of a boson. Large numbers of these pairs can enter a shared quantum state, producing neutron superfluidity. The process is related in principle to the pairing of electrons in a superconductor, though the forces and densities are very different. Superfluid neutrons can move without ordinary viscosity. Rotation is carried through quantized vortices, each containing a fixed amount of circulation. The faster the star rotates, the greater the number of vortices threading the fluid. As the neutron star gradually loses rotational energy, these vortices must move outward for the superfluid to slow. Their motion may not be smooth. Vortices can interact with the crust and with structures near the crust core boundary. They may pin, bend, and release. The sudden rearrangement of many vortices can transfer angular momentum between the superfluid and the visible crust, contributing to the glitches measured in pulsars. The protons in the core may also pair. Because they carry electric charge, paired protons can form a superconducting component. Electric currents may then persist with extremely low resistance. Magnetic fields passing through this material can become confined into thin structures of magnetic flux. But the core is therefore not one fluid, but several interpenetrating quantum components. Neutrons dominate the mass. Protons and electrons maintain charge balance. Superfluid vortices carry rotation. Magnetic flux tubes shape the response of the charged particles. Each component can move differently, yet all remain coupled through forces that are still being studied. This internal complexity can affect how a neutron star cools. Some reactions release neutrinos more efficiently than others. Pairing can suppress certain reactions, while allowing bursts of neutrino emission when pairs form or break. The observed surface temperature, measured years or centuries later, may carry traces of processes occurring deep in the core. Cooling observations have provided evidence consistent with superfluidity, though the interpretation depends on the star's age, composition, atmosphere, and internal reaction rates. The core remains hidden, but not completely silent. Its quantum state influences rotation. Its composition influences cooling. Its stiffness influences radius. Its response to compression influences the gravitational waves emitted during a merger. Each measurement reveals a different part of the same underlying relationship between density and pressure. The outer core may extend through much of the star's radius, containing most of its volume and a large share of its mass. Yet as the descent continues, density rises beyond the range where experiments with ordinary nuclei provide firm guidance. There, the question changes. It is no longer only how neutrons resist being placed into the same quantum states. It becomes a question of whether the matter remains neutron-rich matter at all. Under greater compression, new particles may become favorable. The boundaries of protons and neutrons may become less distinct. Quarks may begin to participate in ways that cannot be described by a simple fluid of nucleons. The physics that supports the outer core is already demanding. The physics of the inner core is where certainty begins to thin. The deeper the descent, the less certain the map becomes. Near the crust, nuclear experiments and well-tested theories provide strong guidance. The density is immense, but it remains close enough to familiar nuclear conditions that physicists can connect calculations with measurements made on Earth. In the inner core, that connection weakens. The density may rise to several times the density found inside an atomic nucleus. Particles are pushed into arrangements that no laboratory can hold for more than a fleeting moment. The material is relatively cold by nuclear standards, trapped by gravity, and allowed to remain in equilibrium for millions or billions of years. No terrestrial experiment creates that complete combination. Particle accelerators can collide heavy nuclei and briefly produce matter at high density. But the resulting material is also extremely hot and expands almost immediately. A neutron star contains matter that has had time to settle, cool, and choose the lowest energy configuration permitted by its pressure and composition. The difference is important. Hot matter may form one collection of particles and phases. Cold, compressed matter may favor another. Observations from colliders can constrain parts of the problem, but they cannot provide a direct sample of a neutron star's inner core. Theory must carry the investigation farther. At the heart of that theory is the strong interaction, the force connected with the structure of protons and neutrons. A proton is not a single indivisible particle. Neither is a neutron. Each is built from three quarks, bound by gluons. The fundamental theory describing those quarks and gluons is quantum chromodynamics. At low energies and ordinary nuclear densities, quarks remain confined within protons, neutrons, and other composite particles. The force between neighboring protons and neutrons can then be described as a residual expression of the deeper interaction among their quarks. It is similar in spirit to the way neutral atoms can still influence one another through the electrical structure hidden inside them. The underlying force acts on smaller charged components, while a weaker and more complicated interaction appears between the composite objects. For nucleons, that residual, strong interaction is powerful. At some separations, it is attractive and helps bind nuclei. At shorter separations, it becomes strongly resistant to compression. This short-range repulsion contributes to the stiffness of neutron star matter and allows it to support masses that degeneracy pressure alone could not sustain. But calculating this behavior at the densities of the inner core is difficult. A neutron star does not contain isolated pairs of particles. Every neutron is surrounded by many others. Protons, electrons, and perhaps muons are present as well. The energy of one particle depends on the states and motions of the particles around it. Two-body interactions matter. Three-body interactions may matter. Collective effects can emerge that are not obvious from studying individual particles. Near ordinary nuclear density, experiments and effective theories constrain these interactions reasonably well. Farther inward, the calculation becomes an extrapolation into conditions that have not been directly tested. Different theoretical approaches can agree near the edge of the core and then diverge at greater density. One may predict that pressure rises rapidly as matter is compressed. Another may predict a more gradual rise. Both may fit the available laboratory data, yet produce neutron stars with different radii and different maximum masses. The uncertainty is not only about the strength of the interaction, it is also about which particles are present. A neutron is slightly more massive than a proton, but inside dense matter, particle populations are governed by total energy rather than by isolated rest masses alone. The particles must satisfy charge neutrality, beta equilibrium, and the Pauli exclusion principle. As density rises, the highest occupied neutron states become increasingly energetic. At some point, creating a different particle may cost less energy than forcing another neutron into the next available state. One possibility involves hyperons. Hyperons are relatives of protons and neutrons. They are also baryons, built from three quarks, but at least one of those quarks is a strange quark rather than an up or down quark. Under laboratory conditions, hyperons are unstable and decay rapidly. Inside a neutron star core, the surrounding matter may prevent the usual decay pathways from proceeding in the same way. At sufficiently high density, hyperons could become stable components of the material. Their arrival would open new quantum states. the overfilled population of neutrons could partly rearrange into a mixture containing hyperons. This may lower the energy of the matter, but it can also reduce the pressure at a given density. The equation of state becomes softer. That creates a difficulty known as the hyperon puzzle. If hyperons appear and soften the material too much, some models can no longer support the heavy neutron stars astronomers have measured. The predicted star would collapse at a mass below objects that are already known to exist. There are several possible resolutions. Hyperons may appear only at densities reached by the most massive neutron stars. Their interactions with neutrons and with one another may become strongly repulsive. Three-particle forces may provide pressure that simpler models miss, or the inner core may change into another phase before a large hyperon population develops. No single explanation has been confirmed. The puzzle does not show that hyperons are absent. It shows that any realistic model containing them must remain stiff enough to support the stars observed in nature. Other particles may also appear. Muons can enter once the electrons have enough energy to make their creation favorable. Various forms of meson condensation have been proposed, in which particles associated with the nuclear interaction occupy a collective quantum state. Each new component changes the bookkeeping of energy and pressure. The deepest possibility lies one level farther down. Protons, neutrons, and hyperons are all hadrons. Their quarks are confined inside individual particles. But as hadrons are pressed closer together, their internal quark distributions begin to overlap. Eventually, the distinction between one neutron and the next may lose its meaning. The quarks may become deconfined. Instead of matter being described as a fluid of separate nucleons, it could become a fluid in which quarks move through a larger shared region. This state is called quark matter. The phrase can suggest a loose gas of independent particles, but the real state would still be governed by the strong interaction. Quarks would continue to exchange gluons and influence one another. The material could organize itself into paired phases, collective states, or forms of color superconductivity. Color in this context does not refer to visible color. It is the name given to the type of charge carried by quarks under the strong interaction. In a color superconducting phase, quarks may pair in a way that changes the material's energy, heat capacity, neutrino emission, and resistance to compression. Whether such matter exists inside neutron stars is unknown. The transition could be abrupt. At a particular pressure, hadronic matter might give way to quark matter through a first-order phase transition. Density could change sharply across a boundary within the star. A mixed region might form, containing structures of both phases arranged according to charge and surface energy conditions. The transition could also be gradual. Rather than a clear boundary, hadrons may evolve continuously into matter, best described through quarks. The identities of the particles would become less distinct without a sudden jump in density. Both kinds of behavior remain possible within current understanding. A strong first-order transition could create two stable stellar configurations with similar masses but different radii. These hypothetical objects are sometimes called twin stars. Discovering such a pattern would provide evidence for a major phase change inside dense matter, but mass and radius alone may not reveal the composition uniquely. A star with a quark core can sometimes resemble one built entirely from hadronic matter. Different microscopic models can produce similar observable properties. This is one reason the inner core cannot be identified through a single measurement. What physicists seek is not only a list of ingredients. They seek the equation of state. An equation of state describes how pressure changes with density and energy. It tells us how strongly the material responds when gravity compresses it further. If pressure rises rapidly with density, the matter is called stiff. Stiff matter resists compression strongly. At a given mass, it generally produces a star with a larger radius and allows a higher maximum mass. If pressure rises more gradually, the matter is called soft. Gravity can compress it into a smaller radius, and the maximum stable mass is usually lower. A new particle or phase often softens the equation of state because it gives matter additional low-energy ways to rearrange itself. But this is not inevitable. Repulsive interactions or changes in the behavior of quarks can stiffen the material again at greater density. A realistic equation of state may therefore change character as the descent continues. It may be relatively soft in one density range and stiff in another. It may pass smoothly between regimes or contain a sharp transition. It must agree with nuclear experiments at lower density, remain stable under compression, and preserve causality so that no physical influence travels faster than light. It must also build stars that resemble the ones astronomers observe. This is where the hidden core reaches outward. The equation of state determines how much a neutron star compresses under its own gravity. That compression determines the radius. It influences the crust thickness, the star's moment of inertia, and the speed of vibrations moving through the interior. During a merger, it determines how easily one neutron star is stretched by the gravity of the other. That deformation changes the gravitational wave signal before the stars touch. The inner core may be inaccessible, but its pressure leaves traces in the motion of the whole star. Across generations, researchers have approached this problem from different directions. Nuclear physicists study collisions and the forces among particles. Radio astronomers time pulsars. X-ray observatories measure radiation shaped by curved space-time. Gravitational wave detectors listen for the motion of merging remnants. None of these instruments reaches into the core. Together, they begin to describe what the core must be capable of doing. The unknown matter beneath the outer core is not free to take any imaginable form. It must support heavy stars. It must produce radii within the observed range. It must respond to tides in ways consistent with merger signals. It must connect with established nuclear physics at lower density. Every constraint removes possible interiors. What remains is a narrowing family of equations, each representing a different answer to the question of how matter resists when compression has passed beyond nuclei. To distinguish among them, the star must be measured from the outside with unusual care. Its mass must be weighed through orbital motion. Its radius must be inferred from light bent around its surface. Its shape must be read from gravitational waves. And through those distant measurements, the pressure in the unseen center begins to take form. A neutron star cannot be opened, sampled, or placed inside an instrument. Its interior must be reconstructed from effects that escape. Light leaves the surface. Radio pulses cross the galaxy. A companion star follows an orbit shaped by gravity. Gravitational waves carry the motion of dense matter through space-time. Each signal contains only part of the answer. When the parts are combined, they begin to limit what the unseen core can be. The first requirement is mass. A neutron star's mass determines how strongly gravity compresses it, and heavy neutron stars are especially valuable. Any proposed equation of state must be able to support the most massive neutron star, known with confidence. If a model collapses before reaching that observed mass, nature has already rejected it. The most precise measurements often come from binary systems. When two objects orbit each other, their masses influence the timing and shape of the orbit. A pulsar makes these systems unusually useful because its rotating beam acts like a distant clock. Each time the beam points toward Earth, a pulse arrives. The interval between pulses can be measured with great accuracy. Small changes in arrival time reveal the pulsar's motion around its companion, the shape of the orbit, and relativistic effects, that would be difficult to detect in most other systems. One of those effects is the Shapiro delay, when the pulsar's signal passes through the curved spacetime near its companion. The path takes slightly longer than it would through flatter space. The delay is small, but it changes in a predictable way as the pulsar moves around its orbit. By measuring that pattern, astronomers can estimate the mass of the companion and the inclination of the system. With the orbital information already known, the neutron star's mass can then be determined. This method has revealed neutron stars with masses near twice that of the Sun. Those objects changed the study of dense matter. Many softer equations of state could not support them. Some models containing new particles predicted that the star would lose stability at a lower mass. The observations did not prove that those particles were absent, but they showed that any theory containing them must also provide enough pressure to keep a heavy star from collapsing. A single reliable mass measurement can therefore remove an entire group of possible interiors. Mass alone is not enough. Two equations of state may support the same maximum mass while predicting different size for stars of more ordinary mass. To separate them, astronomers also need radius. This is much harder to measure. A neutron star may be only about 24 kilometers across, and even the nearest examples are far beyond direct imaging as resolved disks. A telescope sees a point of light, not a visible surface, with a measurable edge. The radius must be inferred from how radiation leaves the star. Some neutron stars have hot regions near their magnetic poles. As the star rotates, those regions move into and out of view, producing pulses of X-rays. The shape of each pulse depends on the size of the star, its mass, the location of the hot regions, and the way gravity bends the light. Near a neutron star, space-time is curved strongly enough that light from part of the far side can bend around the surface and reach an observer. A compact star bends the light more strongly. A less compact star bends it less. This changes how much of the hot region remains visible during each rotation. It also changes the rise and fall of the X-ray pulse. By modeling the pulse shape, researchers can estimate mass and radius together. The calculation must include rotation, the shape of the surface, the pattern of emission from the atmosphere, and the relativistic path of each photon. Different possible hotspot geometries are tested against the data until the combinations that reproduce the observed pulses begin to narrow. The result is not a simple photograph transformed into a measurement. It is an inference built from light, geometry, and general relativity. Observations from the Neutron Star Interior Composition Explorer, mounted on the International Space Station, have made this method more precise. Its X-ray timing measurements have helped constrain the sizes of several pulsars. The emerging picture favors radii of roughly a dozen kilometers for neutron stars across a meaningful range of masses, though uncertainty remains and individual stars need not have identical sizes. That broad scale already carries information. If dense matter were too soft, gravity would compress a typical neutron star into a smaller radius. If it were too stiff, the same mass would occupy a larger sphere. The measured range lies between those extremes. Matter in the core appears capable of strong resistance, but not unlimited resistance. Another clue comes from the star's moment of inertia. The moment of inertia describes how mass is distributed around an axis of rotation. Two objects with the same mass and spin can have different moments of inertia if one keeps more of its material farther from the center. For a neutron star, the moment of inertia depends on both mass and radius, and therefore on the equation of state. In some double neutron star systems, long-term pulsar timing may eventually allow this quantity to be measured through subtle relativistic changes in the orbit. Such a measurement would add another independent constraint on the distribution of matter inside the star. cooling offers a different path. A newborn neutron star releases energy rapidly, first through neutrinos emerging from the interior, and later through photons from the surface. The rate of cooling depends on which reactions occur in the core. Some neutrino-producing processes are relatively slow. Others can remove energy far more efficiently, but they require certain particle populations and momentum conditions. The presence of superfluid neutrons, or superconducting protons, can suppress some reactions, while the formation and breaking of particle pairs can create additional neutrino emission. A measured surface temperature, combined with an estimate of the star's age, can therefore reveal something about its hidden composition. The inference is difficult. The surface may contain a light element atmosphere or a heavier one, and each changes the relationship between interior temperature and observed radiation. Magnetic fields guide heat unevenly. The age may be uncertain. Different internal models can sometimes reproduce similar cooling curves. No single temperature settles the question. A population of stars at different ages can still reveal patterns. Some cool more rapidly than simple models predict. Others remain warm for longer. Together, they test whether the interior contains only familiar nucleons or permits faster reactions associated with different compositions. Rotation also carries information from beneath the crust. Pulsar glitches suggest that angular momentum is stored in superfluid components and then transferred suddenly to the solid exterior. The size and recovery of a glitch depend on how much superfluid participates and how strongly it is coupled to the crust and core. This allows timings measurements to probe the fraction of the star's moment of inertia contained in different regions. A clock-like radio pulse received by an antenna on Earth can therefore reveal the movement of vortices within matter more dense than an atomic nucleus. There is a long human thread in this work. One group builds a detector that will operate for years. Another calibrates the arrival time of pulsars. Another develops a nuclear interaction model. Another compares that model with X-ray light curves or orbital delays. No observer sees the interior directly, yet the measurements accumulate across instruments and generations until some possible stars can no longer exist on paper. The surviving models must satisfy all the evidence at once. They must support heavy neutron stars. They must produce radii consistent with X-ray measurements. They must cool at rates that resemble observed objects. They must allow rotational behavior compatible with pulsar timing. They must agree with nuclear physics where laboratory experiments remain reliable. A model that succeeds in one area and fails badly in another cannot describe the full star. This combined approach is powerful because different measurements depend on the equation of state in different ways. Mass tests whether the material can prevent collapse. Radius tests how strongly it resists compression at more moderate densities. Cooling tests composition and reactions. Glitches test superfluid motion and internal coupling. Each observation removes a different region from the map. Then, in 2017, a new kind of measurement reached the problem. For the first time, gravitational waves were detected from the inspiral of two neutron stars. The signal did more than confirm that the stars were approaching each other. During the final orbits, each star's gravity began to deform the other. The amount of deformation depended on the structure of the matter inside. A larger, less compact neutron star was easier to stretch. A smaller, more compact star resisted tidal distortion more strongly. That deformation altered the orbital motion, and the orbital motion altered the gravitational waves. The effect was subtle, but it placed a new constraint on the equation of state that did not depend on X-ray atmospheres, radio timing, or assumptions about cooling. For the first time, the response of neutron star matter to an approaching companion could be read directly from ripples in space-time. The stars were no longer being studied only while they remained stable and separate. They were being observed. As the balance began to fail, in the last moments before contact, the pressure inside each star was tested by the gravity of the other. Their surfaces stretched, their cores moved. Their orbit accelerated until the two objects merged into a single body, whose mass could lie dangerously close to the boundary of collapse. That final collision offers more than another measurement. It allows the hidden equation of state to shape an event from beginning to end, from the first tidal distortion to the possible birth of a black hole. A binary neutron star carries its final question for millions of years before the answer arrives. The two remnants may begin far apart, circling a common center with periods measured in hours. Each orbit sends a small amount of energy away through gravitational waves. The loss is almost imperceptible at first, but it never stops. The orbit contracts. The stars move faster, the waves become stronger, and the shrinking accelerates. Long before detectors could hear those waves directly, pulsar timing revealed this process. A neutron star in a binary system acted as a clock, and its changing orbit matched the loss of energy predicted by general relativity. The stars were not simply moving around each other. They were descending through space-time toward a collision. In the final minutes, the scale of the motion changes rapidly. Two spheres only a few dozen kilometers wide may orbit hundreds of times each second. Their surfaces move through a gravitational field produced by more than a solar mass on either side. The stars are still separate, but neither is isolated any longer. Each one raises tides on the other. A neutron star is compact, yet it is not perfectly rigid. The gravity of its companion stretches it slightly along the line between them. How much it deforms depends on the equation of state. A larger star with matter that resists compression in one way may develop a different tidal response from a smaller, more compact star. That response alters the orbit. The orbit shapes the gravitational waves. By the time those waves reach Earth, the tiny deformation of matter, more than 100 million light-years away, has been written into their phase. This quantity is called tidal deformability. It does not identify every particle in the core, but it helps determine which combinations of mass, radius, and pressure remain possible. Then the surfaces touch. The contact does not create an ordinary impact between solid bodies. The crusts fracture and merge. Fluid cores shear past one another. Shock waves heat the matter. Magnetic fields are wound and amplified. Some material is squeezed inward, while some is thrown outward into expanding tails and clouds. For a brief interval, the system contains too much motion to resemble any settled star. The fate of the central remnant depends on its total mass, the amount of angular momentum it carries, and the equation of state of its matter. If the merged object remains below the maximum mass that a non-rotating neutron star can support, it may settle into a heavier but stable neutron star. If its mass lies above that non-rotating limit, rotation can provide temporary help. Uniform rotation can support an object somewhat heavier than the ordinary limit. Such a remnant is often called supramassive. It may survive while it spins rapidly, then collapse later as radiation and magnetic torques carry angular momentum away. A still heavier remnant may be supported by differential rotation, with inner and outer regions turning at different rates. Thermal pressure from the merger also contributes for a time. This object is called hypermassive. Its support is temporary by definition. Magnetic stresses and turbulence work to reduce the differences in rotation. Gravitational waves carry energy and angular momentum away. Neutrino emission cools the remnant. The extra forms of support weaken and the central density rises. The collapse may follow in milliseconds, or the remnant may persist longer before crossing the boundary. If the combined mass is high enough, even differential rotation and heat cannot delay the outcome. an event horizon forms promptly after the collision. Much of the central matter disappears behind it, while material with enough angular momentum may remain outside in a hot accretion disk. These outcomes are not separated by one universal mass that applies without context. The maximum mass of a cold, non-rotating neutron star is one boundary. Rapid uniform rotation raises the allowed mass. Differential rotation can raise it further for a short period. The threshold for prompt collapse in a merger also depends on the radii and internal structure of the original stars. This makes every merger a test of support under changing conditions. Before contact, the stars reveal their tidal response. At contact, the matter is heated and compressed. After contact, the lifetime of the remnant reveals how much temporary support rotation and thermal energy can provide. If a black hole forms, the timing of that collapse carries information about the point at which all forms of resistance failed. On August 17, 2017, this sequence became observable in several different ways. The gravitational wave signal known as GW17081 Swanson arrived first. It had been produced by two compact objects spiraling together in a galaxy about 130 million light-years away. The long in spiral and the measured masses identified the system as a neutron star binary. The final part of the signal constrained the tidal deformability of the stars. They could not have been extremely large and easily distorted, but the measurement did not select one unique equation of state. It narrowed the range. Less than 2 seconds after the merger time, satellites detected a short burst of gamma rays from the same region of sky. The delay connected neutron star mergers with at least some short gamma ray bursts, but it did not provide a simple stopwatch for the lifetime of the central remnant. The launch of a jet, its movement through surrounding debris, and the angle from which it is viewed can all affect when gamma rays become visible. The remnant of GW170817 may have formed a black hole quickly, or it may have survived for a short interval as a massive neutron star. The available evidence places useful limits on the possibilities, but the exact sequence inside the first moments remains under study. Hours later, telescopes found a new source of light in the host galaxy. It was a kilonova, material ejected from the merger, expanded through space rich in neutrons. Atomic nuclei captured those neutrons rapidly, producing heavy, unstable nuclei that later decayed. The energy from those decays heated the expanding debris and powered light that changed in brightness and color over the following days. This process is called rapid neutron capture, or the R process. It can build elements heavier than iron, including nuclei in the regions of the periodic table associated with gold, platinum, and uranium. Spectra from the kilonova linked to GW1N081 later revealed strontium, providing direct evidence that heavy element production had taken place in the ejector. The glow did not come from the central object alone. It came from matter that escaped. Different parts of the ejector carried different compositions and histories. Some material was pulled away by tidal forces. Some was driven out by shocks. Additional matter could leave the disk through winds shaped by neutrinos, magnetic fields, and nuclear heating. The color and timing of the kilonova reflected these differences. Material with fewer heavy lanthanide elements allowed bluer light to escape earlier. Material richer in lanthanides absorbed light more strongly and released more of its energy at red and infrared wavelengths. The kilonova therefore added another layer to the measurement. It offered clues about how much matter was ejected, how neutron-rich it was, and how long the central remnant may have influenced the surrounding disk. Gravitational waves described the inward motion. Gamma rays revealed a relativistic outflow. Visible and infrared light followed the newly formed nuclei. X-rays and radio waves later traced the jet as it interacted with material around the system. No single messenger contained the whole event. Together, they turned one merger into a study of gravity, nuclear reactions, magnetic fields, and dense matter. There is a present-day stillness to the way these signals are received. A detector rests in its vacuum system. A mirror moves by less than the width of a proton. Software marks the passing wave. Elsewhere, telescopes turn toward a patch of sky and collect photons that began their journey at the same collision. The instruments do not touch the neutron stars. They record what the stars surrendered. From that record, physicists ask whether the matter was stiff or soft, whether the remnant survived briefly or collapsed promptly, and how much mass remained outside the final compact object. Future detections may carry a clearer signal from the remnant after contact. High-frequency gravitational waves from a short-lived hypermassive star would contain oscillation patterns shaped by its radius and internal composition. A sudden end to those patterns could mark the formation of a black hole. Current detectors are most sensitive to the earlier in spiral. The post-merger signal lies at higher frequencies and is harder to measure. More sensitive observatories may eventually follow the balance through its final milliseconds. Until then, the merger leaves a boundary drawn in several kinds of evidence. Below one mass, a neutron star can remain. Above another, collapse is prompt. Between them lies a temporary star supported by rotation, heat, and motion that cannot last for most of its life. A neutron star resists gravity through the properties of cold, dense matter. During a merger, it borrows support from the collision itself. And when that borrowed support is spent, the hidden limit becomes visible in the formation of a horizon. A neutron star can survive only while a stable solution still exists. That statement sounds mathematical because it is. The star does not remain intact through effort, intention, or a hidden reserve of strength, tie. It remains because its mass, pressure, density, and curvature can still be arranged in a self-consistent form. Physicists describe that arrangement with equations first developed for relativistic stars in the late 1930s. They are known as the Tolman-Oppenheimer-Volkoff equations. These equations ask how pressures change from the center of a compact star to its surface, while general relativity is fully taken into account. They include the gravitational influence of mass, energy, and pressure itself. They follow the way space-time becomes increasingly curved toward the center. To solve them, one additional ingredient is required: the equation of state. For every possible equation of state, the calculation produces a family of neutron stars. One model may begin with a relatively low central density and form a lighter star. Increasing the central density produces a heavier one. The radius changes, the pressure rises, the entire interior reorganizes. For a time, adding density adds mass. Then the sequence reaches a turning point. Beyond that point, a higher central density no longer creates a stable, heavier neutron star. The mathematical branch bends away from stability. Small disturbances no longer settle. Compression encourages further compression. The maximum mass on the stable branch is often called the Tolman-Oppenheimer-Volkoff limit. It is not one number known in advance. Its value depends on the equation of state, and the true equation of state remains uncertain. Different forms of dense matter resist compression differently. A stiff interior can support more mass. A soft interior reaches instability sooner. The lower boundary is set by observation. Neutron stars near two solar masses are known to exist, so the true maximum cannot lie below them. Whatever particles or phases appear in the core, their combined pressure must be sufficient to support those stars. The upper boundary is constrained by relativity and causality. The material cannot become arbitrarily stiff. Information and disturbances cannot move through it faster than light. General relativity also ensures that increasing pressure strengthens the gravitational field that pressure must oppose. The true limit is therefore expected to lie not far above the heaviest measured neutron stars, though its exact value has not been fixed. A neutron star approaching this boundary would not necessarily look different in an obvious way. Its surface could continue rotating. Its magnetic field could continue guiding particles into beams. Radio pulses might still arrive with clock-like regularity. The instability would be hidden in the relationship between the center and the rest of the star. The central density would be higher. The radius might be smaller. A greater share of the star's mass energy would be bound by gravity. The escape speed from the surface would move closer to the speed of light. Even then, the star would remain a star. It would have a material surface. Light could still leave, although strongly redshifted by gravity. Matter could still strike the crust. Signals from the surface could still travel outward. A black hole is not simply a neutron star with greater density. The distinction is an event horizon. As long as no horizon exists, the star's surface remains in causal contact with the universe beyond it. Once a horizon forms, the interior can no longer send information outward. The transition may occur rapidly. Imagine a neutron star receiving matter from a companion. Gas spirals through an accretion disk and settles onto the surface. Most of the added material is only a small fraction of the star's total mass, but the process can continue over long periods. The star grows heavier. Accretion may also spin it faster, allowing rotation to provide additional support. For a while, the star can remain above the mass that a non-rotating neutron star could carry. This creates a delayed boundary. The object may survive while rotation remains rapid. As it loses angular momentum, the additional support weakens. At some point, the star can no longer remain on a stable rotating branch. Collapse follows even if no new matter arrives. This possibility is sometimes called a supramassive collapse. The same principle appears after mergers. A remnant may survive because differential rotation and thermal pressure temporarily hold it above the cold, non-rotating limit. As those temporary supports fade, the object crosses into a region where equilibrium is no longer available. The central density rises. The inward motion strengthens. A trapped surface forms. The event horizon appears before all the matter reaches the center. From outside, the newly formed black hole is described by a small set of measurable properties, mainly its mass, rotation, and electric charge, which, in astrophysical settings, is expected to be very close to neutral. The detailed layers of the neutron star no longer remain visible. Its crust, superfluid vortices, magnetic structures, possible hyperons, and possible quark phases pass behind the horizon. Their complexity is not destroyed in any ordinary sense that can be watched from outside. It becomes inaccessible. The collapse, therefore, marks two endings at once. It ends the material support of the star. It also ends the possibility of observing that material directly through signals escaping from its surface. This is why the maximum mass matters so deeply. It is not only the heaviest weight a neutron star can carry, it is the last point at which ultra-dense matter can remain visible to the universe. Below the limit, quantum mechanics and nuclear interactions still shape an object with a surface. Above it, those same particles continue inward within a region from which no outward message can return. The boundary is physical, but it also marks the edge of what observation can reach. For generations, researchers have approached that edge from different sides. One measures the slow delay of a pulsar signal passing near a companion. Another studies X-rays curved around a rotating surface. Another calculates how nucleons interact when packed close together. Another listens for the final seconds of a binary in spiral. Each method touches only part of the star, yet together they tighten the space in which the unknown interior can hide. There is something measured and patient in this kind of progress. The equations do not suddenly reveal a complete answer. Observations do not arrive with labels identifying the particles in the core. Instead, one possible equation of state becomes less likely. One range of radii narrows. One maximum mass moves slightly upward or downward. The hidden star is reconstructed through exclusion. It cannot be too small. It cannot be too large. Its matter cannot be too soft to support the heaviest pulsars. It cannot be so stiff that causality is violated. Its tidal response must fit the waves recorded during inspiral. Its cooling must remain compatible with the temperatures seen at different ages. The remaining possibilities become fewer. Perhaps future gravitational wave detectors will measure the oscillations of a merger remnant before it collapses. Perhaps a pulsar will be found with a mass close enough to the true limit that many remaining models fail at once. Perhaps more precise X-ray observations will reveal a sharp change in radius at a certain mass, suggesting a phase transition in the core. Perhaps no single observation will decide the question. The answer may emerge from many small constraints brought together over decades. That would be fitting. A neutron star itself is held together by many effects acting at once. Its explanation may also require many forms of evidence meeting in one place. For now, the maximum mass remains hidden somewhere above the heaviest stable stars we know, and below configurations that relativity will not permit. It is not a line drawn on the surface of any object. It is a limit written into the behavior of matter and space-time. Every neutron star lives below it. Every stellar mass black hole formed from collapsing dense matter lies beyond it, and between the outcomes is a narrow region where pressure, rotation, temperature, and compositions decide whether the universe keeps a surface or closes it away. The question that began with collapse ends with balance. A neutron star remains because matter has not yet reached the point where every possible form of support fails. The collapse of its parent star destroyed atoms, consumed most free electrons, compressed nuclei, and forced the surviving core into a state unlike anything found on Earth. But gravity did not erase structure completely. It replaced one structure with another. Near the surface, nuclei and electrons form a rigid crust. Farther down, neutrons move beyond the boundaries of nuclei and enter a superfluid state. In the outer core, quantum statistics prevent the particles from settling into identical states, while nuclear interactions add resistance at short distances. Deeper still, the composition becomes uncertain. Hyperons may appear, quarks may move beyond the boundaries of individual neutrons. A phase transition may divide the core into regions with different forms of matter, or the entire interior may remain connected through a gradual change that leaves no clear boundary at all. These possibilities sound different, but every viable one must answer the same demand. It must produce enough pressure. Not pressure from heat alone, not the ordinary pressure of particles colliding in a container. The support comes from the quantum states available to fermions, from the interactions among nucleons, and perhaps from the collective behavior of matter in phases that have never been isolated on Earth. All of it must operate within curved space-time. General relativity does not allow pressure to stand outside gravity as a separate opponent. Pressure contributes energy, and energy contributes to curvature. The support strengthens the field it must resist. This is why a neutron star cannot grow without limit. At lower masses, stable arrangements exist. The star may cool, slow its rotation, and remain intact for longer than many ordinary stars continue shining. Its interior pressure adjusts to its density, and the structure stays on the stable branch of possible solutions. As mass increases, the center is compressed more strongly. Particles are forced into higher energy states. Nuclear interactions become increasingly important. new particles or phases may appear. The radius, central density, and gravitational binding all change together. Eventually, the sequence reaches a point where greater compression no longer creates another stable star. Beyond that point, no rearrangement can restore equilibrium. The collapse does not happen because quantum mechanics suddenly stops applying. The exclusion principle remains true. Nuclear forces remain present. The particles continue to follow the laws that governed them before. They are simply no longer enough. Gravity has reached a strength for which no known configuration of matter can provide the required response. An event horizon forms. The surface that once released light and particles is removed from contact with the surrounding universe. The layered interior, with all its uncertain phases and quantum fluids, passes into a region that cannot send information outward. The neutron star becomes a black hole. Between these two objects lies one of the clearest boundaries in nature. On one side, matter still has a surface. It can rotate as a body, support magnetic fields, crack, cool, emit radiation, and be measured through the motion of a companion. On the other side, the horizon replaces the surface as the defining feature. The exact position of this boundary remains unknown because the equation of state remains unknown. The heaviest measured pulsars tell us that dense matter can support at least about twice the mass of the Sun. X-ray pulse profiles constrain the radii of several stars. Gravitational waves reveal how neutron stars form before a merger. Each observation removes possible answers. None has yet provided the complete one. This incompleteness is not a weakness in the study of neutron stars. It is what makes them valuable. They connect fields of physics that are often studied separately. Quantum mechanics governs the allowed states of particles. Nuclear physics governs the interactions among those particles. General relativity governs the space-time containing the entire star. Inside a neutron star, all three are required at once. A pulsar timing signal can test gravity. A radius measurement can constrain nuclear matter. A merger can reveal how an unknown quantum fluid responds to tides. The star becomes a meeting place for theories developed at very different scales. What happens inside a region only a few dozen kilometers wide can illuminate the behavior of quarks, the structure of nuclei, and the formation of horizons. The measurements may continue to improve gradually. A new heavy pulsar may move the lower bound on the maximum mass. A more precise radius may exclude another family of equations of state. A future merger may produce a detectable post-collision signal, allowing astronomers to follow the remnant as it oscillates, settles, or collapses. A pattern across several events may reveal a sudden change in structure at a particular mass. The answer may not arrive as one dramatic discovery. It may appear as a narrowing interval. A range of pressures becomes smaller. A set of possible radii contracts. One phase transition remains compatible with the data while another does not. The maximum mass approaches, a value that different methods begin to share. This is how an invisible interior can become known, not by entering it, but by learning how every possible interior changes what the star does outside. For now, a neutron star remains partly hidden. Its crust can be modeled, but not touched. Its superfluid can be inferred, but not watched. Its core can be constrained, but not named with certainty. Still, the object itself confirms something profound about matter. Under enough pressure, atoms disappear. Under greater pressure, nuclei lose their boundaries. Yet, even after these transformations, matter can continue to resist. It can organize itself through quantum rules and nuclear interactions into a star smaller than a city, heavier than the sun, and stable enough to outlast civilizations. The survival is not permanent in every case. Accretion can add mass. A merger can combine two remnants. Rotation can slow. Temporary support can fade. At some point, the final stable arrangement may be lost. But until that threshold is crossed, the star remains present in the universe, turning beneath its magnetic field and carrying the record of a collapse that stopped just before the horizon formed. Across the galaxy, some neutron stars announce themselves with radio pulses. Others glow faintly in X-rays. Some may have cooled until they are almost impossible to find. Their interiors continue to hold the same balance, whether anyone observes them or not. Gravity presses inward. Quantum states fill. Nuclear matter pushes back. Curved space-time contains the whole structure. And within that structure, the universe preserves a form of matter, poised at the last stable distance before disappearance. The star keeps its surface beneath the weight of itself.